Okay, welcome back to today's lecture. And today we would be starting with continuity. Yesterday we had discussed about functions, what are domain, what is the range. So in short, I'm just revising domain are all the values which a function can accept. That means the input values, and range are all those values which a function gives as the output. So the concept of domain and range we had already talked about. We talked about what exactly functions are. That means um any mapping from set X to set Y with every domain having a unique image in the range. So this was the definition of functions which we had already discussed in a previous lecture. So now let's start with another important concept which is called as continuity. So continuity. What exactly is continuity? If we see in normal terms, something that is continuous, something that is not having any breakage or discontinuity, that is called as being continuous. So it is exactly the same concept which we are following in this, and we have to check out whether a function is continuous at a point or not. That means, in layman's term, being continuous means having a value for a function. So let's start. So we are having some graphs and we'll try to understand with the help of graph. Before that, I want to tell you the definition of what exactly continuity is. So we say that, see, there are two things. First of all, you need to know being continuous always has some predefined laws, and there are three pointers which you need to take in your account. That is a function f, where f can be any function. F equals to sine x, cos x, x square, y square, not y square. Yeah, it can be y square also if you're taking f of y equals to y square. So it can be anything, any function in any values which you're talking about. So a function is called continuous at x equals to a. So whenever we need to check continuity, we need to define a point so that then only we can check at that point whether the function is continuous or not. So some key pointers again are a function f is continuous at x equals to a if my f at a is defined, my limit fx where x tends to a exists, and the third one being limit fx equals to fa at x tending to a. Now second and third are somewhat not actually clear if you see just from the definition, that I'll try to make you understand through examples. And the last line says if any one of the conditions is not met, the function is not continuous at x equals to a. So this is an important concept where you need to note that at x equals to a is an important. So now you're seeing these two eggs, which are not eggs actually. They are my two sets, say x and y. Now we have already learned that every mapping from this set x to set y is there, and it will be called a function if for every value in x we are having some unique image in y. So let's assume we are having some term, say small x here. This is capital X. This is capital Y. We are having some small x here. And we are having another term, say A here. So the definition for continuity says that limit definition I'm talking about. That whenever x tends to A, that means whenever you are tending to A, that whenever I'm moving towards A, I would be getting for my x an equivalent fx in my y set, which would be my range set. This is all the values here are in domain in X, and all the values here are my range values. That is what we actually got to learn about from the definition of functions. So for every X, I would be having an fx, equivalent fx in my set Y, and for every A, I would be having an equivalent fa, where when I am tending towards A, when I'm moving towards A from X, then my function would also move towards A. That means for every value of X which tends to A, my A is a point. It is called actually limit point. This you will get to know when you study higher mathematics. So whenever my X tends to A, I'm having an equivalent image of X, which is Fx, and equivalent image of A, which is Fa, into my set Y, such that my fx always tends to A when X is tending to A. So this was exactly the thing. And you can see there's our unique images. So this is as per the definition of a function. So this was from that point of view. Now talking about in short term what exactly continuity is, you need to check three things. That means limit of a function fx when X is tending to A negative. A negative means you're moving to a point A from the negative side. Let's say we are having a scale here, and here is my point A. So if you are coming from the left hand side, you know that from if you're coming from the left, you're having negative values. From like if this is the x-axis and A point is equals to 0. So if you're coming from left, you're coming from negative side of the x-axis. So this concept only need to take into in my consideration. And here I would be having some A negative, some very small value or very close value actually to A, which is called as A negative. And moving towards the right, I would be having some A positive, right? So I say if the limit of my function fx when I am coming from a negative side, that is from the left hand side, that is extending to a negative, should be equivalent to limit of function fx when x is tending to a positive. That means I'm coming from the right hand side, that is the positive side of a I'm coming from. This should be equal to the value of the function at A. So at A, this should be equal to the value of the function at A. This is exactly this point which you would be getting. So let me tell you about this thing from the graphs which are given here. You see, this first one, this function is being called continuous at all x. At all values of x, you can find some value of y. This was only we talked about here in this 2x, which I told you about the set. For all values of x, you can find a corresponding value of y. This fx was nothing except y. This is the value which I'm getting as my range. So for all values of x, which you are having, you can see for all values of x on my, this is the x-axis. For all values of x, I'm getting every value of y. And this value are actually unique because if you make vertical line along this, you will never get the vertical line crossing to 2 points. Then only it is a function, and you can check continuity of function. So this is continuous because it is having values at all the points. Now see here, this second one, I'm talking about this one, this second graph at every value of x, it is giving some value of y. My y is given here as this point. But at my point A, I am getting a hole. Hole means there's no point actually which is mapping to y. That means for x equals to a, I'm not getting any point on the my y-axis to tell me that, okay, this function is defined. So this function is not defined at x equals to a because you are getting a whole. And you can see here, this is fa. For every a, you get a corresponding fa. And fa you will get on y because it is belonging to the y set. This only I made it clearly through the two eggs or the two sets. So this is the thing. Now, why it is called as removable discontinuity? Removable discontinuity means whenever you are moving from a negative side, that means whenever you are moving from the left hand side of A, and whenever you are moving from a positive side, that is coming from the right hand side of A, then you can get very close value, not at A, but in the surrounding or in the neighborhood of A, which will have some value in the y-axis or the y mileage. You can see if I move at the outer circle, I'm getting very small values which are close to it, but I'm having this function is defined at a negative and it is also defined at a positive, but this function is not defined exactly at a. That is why it's called as removable discontinuity, because we can, if we define some value at A, then my this condition, which I had already told you about, will be true. That is, limit fx when I'm tending coming from a negative should be equals to my function when I'm coming from a positive should be equivalent to the exact value of that function when x equals to a. So you're getting f a. So this was the thing which they are talking about. That is why they have called about removable discontinuity. Again, the same example they have given you in this third one also. You see about fourth one. This is called as jump discontinuity. You are having every value of y for corresponding to a x, but at point A, you are seeing that you are not having a value for y. You see, there is a hole here, but if you see closely, you are having a filled hole here. That means you are having a value for x equals to a in your y-axis. That means in your y set, you are having the value exactly. But this you are not getting right here. If this thing has rightly jumped from this point to this point. So this is called as a jump discontinuity. When you're actually jumping, there is a break in the graph pattern, but you're actually having some value of a. It's not that your function is not defined at a, but having some value. Infinite discontinuity means when at a your function or your function tends to infinity. When at a your function is tending to infinity. If you see this graph is tending towards infinity, this graph is tending towards infinity. Like the graph of log, it tends to infinity. Graph of I give you example that will help you to understand. Let me come here. So this was the term which I had already explained to you about. This you should remember. This is the mathematical definition of continuity. That means limit when you are coming from a negative, limit of function when you're coming from a negative should be equivalent to limit fx when you are coming from the a positive side should be equals to the pointer. So this I'm making cloud. You need to note down in your copy so that you're actually having the things. So now let me just give an example about how exactly your thing should be. Now I talk about I'm making my x-axis and y-axis. This is my x-axis and the y is this one. And I'm also making a line here, this one. But point to be noted is that I take my pen, I take my white pointer here, and I push a punch a hole here. Let me just punch it. Oh, it's not punching. I need to take larger shades. Let me punch a hole at x equals to 0. So I hope it is clear that I have a hole at x equals to 0. Yeah. So now it's clear. So this is my x-axis. This pen pointer should be, so this is my x-axis. This is my y-axis. This is my line which is actually going here. And you see, this is my origin, x equals to 0 or y equals to 0, x and y equals to 0. So this is my line which is actually moving from this pattern to this pattern. So my question is this graph continuous? So first thing, what you need to check, you need to just go to your definition which was given to you actually. And this is your definition which we were talking about. Now check everything. It says f is continuous at x equals to a. So first of all, in question, you need to find out about which point they are talking about to look at for the continuity. If they are talking about that, you need to check the continuity, say for point -3 or say for point 3. So at that point, you're having a corresponding value on the y-axis somewhat here. This for now, this is what is it is exactly. This is the y-axis, which I can tell as fx. So for f equals to 3, I am getting f equals to 3 here. Some value for my 3 I'm getting equals to equivalent to here. For my f equals to -3, again I am getting some value. I'm not getting value above, I am getting the value below. So this, because my graph is here. So I am getting some value on my y-axis, which is called as f of -3. So at point minus 3 and at point 3, my graph is continuous because I am satisfied with my first property that my FA is defined. Yes, for every A, you are getting a corresponding FA. That is true. And second point, limit x equals to a fx exists. Exactly, it exists because when you are coming from the left-hand side of this graph, you are having some value because it is all defined here, if you see here. And when you are coming from the right-hand side, that is the a positive side, again, you are having some value because it is a continuous graph. It is having every value of fa present. So it is actually continuous at x equals to 3 and x equals to minus 3. But what if I am asking you that is this graph continuous at x equals to 0? You need to tell me that is this graph continuous at x equals to 0? You can stop the video right here and think about that is it continuous or not. So it is not continuous. I tell you why. Because if you see from the definition at x equals to 0, if you see the first pointer here, am I getting some f0? No, I'm not getting any value of f0 because you see there is a hole punched there. That means for at 0, my function is not defined because I'm not having any value present for the value of x at 0 in my y. That means I am having no f0 present in my range set y, which I had shown you in those two eggs. Sorry. So this was the whole concept about continuity. Now, this is how graphically you found. What if you are given some question saying that let's take your this and tell me is 1 by this is fx. This is my function given to you. It says fx equals to 1 by x and tell me whether this function is continuous at x equals to 0 or not. Okay. So what are the 3 points you need to see? You need to check by this definition, which I already told you. And what is the definition? You can check by this definition also. But first, FA is defined. Okay, checking the first property. Is FA defined? Whenever you put x equals to 0, you will be getting infinity. So infinity is not defined actually. So from your first definition only, you are knowing that this function is not defined at x equals to 0. But this is not how you can prove mathematically. You cannot write English into maths and prove that, okay, this is not defined. You need to show. So how we will show that this thing is not defined? We will show by using this thing. So I'm moving it for you to that point so that we can get it and we can have it there. Okay, I want the whole of the thing. So I'm getting it here. Okay, so let's count it. It says this is how you will prove it mathematically. You know verbally and you know mentally that this is not actually defined. This function is not defined at x equals to 0 because when the moment you put x equals to 0, anything divided by 0 tends to infinity. And infinity is not defined. It is from alien world. So you need to check. So first we will check limit fx. Okay. So let me get my pen out to show you. Let's use blue color. First, I will say limit. My function is fx. Instead of fx, I'm putting 1 by x. And at what point I need to check? I need to check at a negative. A negative here, a is 0. Here a is because x is equals to a. So here my a is 0. So I will first check at 0 negative. So 0 negative means if this is my number line and this is 0. So if I'm coming from the negative side of my x-axis, so the moment you put a 0 negative value, that means a very 0 is 0, but some negative value very close to 0, very, very close to 0. Some negative means towards the left hand side of 0. So the moment you put that, you will be getting minus infinity. That means you will be going to infinity from the negative side because you are coming from the negative side. You're coming from 0 negative. So that is you're coming from negative side. So this is first thing we're getting minus infinity. Now for the second portion that is limit. Again, my function I put as 1 by x. Now I need to check when you are coming from 0 positive side, that is the right hand side. So the moment you are putting 0 right here, 0 positive means some value close to 0 coming from the positive hand side of the x-axis towards the 0. So you are getting a plus infinity. That means you are going to infinity from the positive side. You know why I'm talking about this? Because if this is my arrangement, you are coming like this, your graph is taking some point, and whenever you are coming to zero, you are tending to infinity, positive in infinity. And when you are coming from the negative side, that is zero negative, you are going to negative infinity. Okay. And you already know that at x equals to 0, your function is not defined. That means at f equals to fa is f0. At f0, whenever you put fa, my a is 0 here. So the moment you put 0 in this function, 1 by 0 is infinity. So if you see here, there are three different things. Now at f equals to a, that is at f equals to 0, I am getting a infinity. So this function is not actually defined. So mathematically, you have proved that this thing is not equivalent here. This is not holding. This all cloud work which you had known previously, this is not holding for this function. So you'll call this that 1 by x is not continuous for x equals to 0. Now my question is my function fx continuous for the whole real line except 0? Yes, it is true, because we know already that it is having all the values. No matter what values of x you put, you will be getting some value of y. So yes, my function is continuous for all real values except 0. Except 0 is a very important point, because at 0 you have already proved that this function is not continuous. This function is not continuous at x equals to 0. So this we have already proved, and this was the crux of the whole definition of continuity. So I hope you are able to understand about what continuity is. So removable discontinuity, we have already talked about. Jump discontinuity, we have already talked about that you're getting some value, but we have redefined it to fa. Infinite is tending towards infinity, that is 1 by x, just shown to you. Now here is the definition of continuity. It says a function f is continuous at x equals to a if limit fx equals to f. I've already shown you in that picture where I have listed 3 points differently for you, so you can note just that thing. Now let's come to different example. It says judging from their distance graphs. Okay, graphs. Coming from the graphs, they are saying tell us whether they are continuous or not. So seeing from the first point, this is x1, this is x2, this is x3. So you see that at point x, this lower portion is tending towards negative infinity, and at point x equals to 3 or x equals to 2 something, it is tending to positive infinity. So this function is not defined at this interval or this point, because the points are not exactly defined in the graph, but you know that at this point or in this interval, small interval, this graph is tending towards infinity, going down, going up straight. So it is tending towards positive infinity and negative infinity from the left and right hand side of the graph. So this function is not continuous at this point, this exact point, the line where I have made, or the interval which I have made, the small interval that is given to you, because in that interval only the graph is forming some asymptote. Asymptote means it's tending to infinity. Now, this thing is about you see, if for every value of x you are having some value of y, and this is a parabolic shape, which means some quadratic equation is there. X square function comes like this and goes from origin like this up, parabolic function. So this is some quadratic equation only, whose graph has been made. That is why it's shifted from the origin. So this is a continuous. This is actually continuous in all values of r. While this one, first one is not continuous at all the values, because it is discontinuous at this interval or line. Now coming here, this function is continuous at all the values except this whole. And about the whole, which I have already told you about, that means at x equals to 2. This is x equals to 2. At x equals to 2, this function is not having any value of y, any corresponding value of y. That means this function is not defined at x equals to 2. And when you know that this function is not defined, you break the first rule of continuity. That means fa should be defined. So this is how you are actually finding out the continuity and what exactly it is. So I hope you have understood about all the concepts of continuity, and it is a very important concept. Later on in our class, we will be dealing with some more examples of continuity. So that's all for today. I think I should cover increasing and decreasing functions and their boundedness in the next lecture. So meet you in the next lecture. Till then, have a great day.